Hello, everyone. I'm Eiji Shibata from SUBARU Japan. And this presentation, I will explain our activity of the improving road safety with AI-based stereo camera object detection. And this is technical presentation. I'm sorry. And please. Go ahead. I will start. And this is overview of our company. Our main business unit is automotive. We have many unique technology. Sorry. And we have many unique technologies such as symmetrical AWD and stereo camera called eyesight. In this session, I will focus on what kind of technologies the stereo camera consists of and how it will evolve with AI. This slide shows our philosophy. Our corporate social responsibility is to achieve zero fatal accidents. We are tackling this goal with the safety technologies we've been developing and our DNA as an aircraft manufacturer. And I believe the key to achieve zero fatal accidents is the sensor, stereo camera. We have been developing in-house stereo camera for over 30 years, very long history we have. From planning to circuit board prototyping and software coding, and vehicle testing, almost everything. This in-house development is our strength. I show an example in the video. I'm showing the raw data that was actually recorded by eyesight, not created manually. This data creates eyesight inside. You can see that the objects are detected by a very large amount of point cloud data. So, for example, our system can detect vehicles which cut into the lane very accurately. Here is the basic principle of our stereo camera technology. The stereo cameras have two cameras, right and left. They are in different places, so they capture different viewpoints. We call the difference disparity and convert into distance. So the algorithm calculates an object distance based on triangulation. It's a very simple structure. I will explain our object detection method. The strength of our method is that it can detect objects using only distance. We call this general object detection. And the disparity image at the upper left shows everything in 3D scene, disparity image. Our algorithm first finds the road surface, and next light image. Then everything above it is an obstacle in the car's driving environment. That's seen as the disparity index at the lower left image. By applying grouping, we identify all the obstacles to the car. And impedance. Thank you. So, how will this algorithm evolve with AI? The image shows an example. You can see everything in 3D by depth information. But you only understand the size, shape, and the position, and you cannot understand what it is from depth information alone. AI will add more information. For example, the purple means the roads, pink means the sidewalks, and this feature will help better recognition. Now, I would like to talk about the general development trend in cars and AI. There are many objects that must be detected in the driving situation, such as other cars, lanes, and traffic lights. In addition, the semiconductors need to operate with very limited power consumption and should be low cost. Therefore, highly integrated and efficient multitask network structure is often used. And here is a diagram of our AI architecture. We have developed our own multitask network where over 20 heads, such as object detection, road marking detection, depth estimation, and segmentation, share a single backbone. We call this SUBARU AstraNet. And let's watch the video of SUBARU AstraNet. The drivable area is green, road marking, stop lines, traffic lights, and cars are also recognized at the same time. From here, I will explain how AI and stereo cameras are a very good combination. The upper left image is an AI road segmentation image of a hill in San Francisco. Even if the road structure is very complex, the CNN structure can help classify each pixel based on its surrounding context. This is the strength of AI. Meanwhile, our stereo camera can also calculate disparities for each pixel. It means that the disparity image from stereo cameras and the AI segmentation can be matched pixel for pixel perfectly, because they are from the same image source. On the other hand, a system that combines different sensors, such as a monocular camera and LiDAR, does not work. I'm sorry. Does not work like this because the fusion from different sensors is not so easy. This is the reason I believe the AI stereo camera is best. Of course, AI is not perfect. For example, AI learns from training data, so the performance is lower in unknown situations. This is an example. It's not difficult to detect a pedestrian in the urban road's background, because it's a normal situation. However, if I put the same pedestrian in the highway background using CG, the detection score will be low. Light image has similar problem. There are fundamental problems with AI. So, what can we do? We use the stereo camera and AI to complement each other. These are CG images with a person lying on the road. Of course, there are rare situations, but the stereo camera can potentially detect everything, even for the first time. But stereo cameras does not recognize what it is. It could be an obstacle to stop at, or just a bump to climb over, AI can classify it. So by combining the stereo cameras and AI, we can realize more reliable and robust sensors. This is our way. From here, I would like to talk about another topic, the challenge for applying AI to autonomous driving. The typical AD-ADAS systems are designed to be used on highways. However, there are various challenges in applying the system to urban roads. What's the difference? The essence of the problem is here. The physical parameters for steering control are different between highway and urban roads. On highways, the target steering angle is directly decided by the curvature of white lines. But on urban roads, what should be the physical parameters that is highly correlated with the steering angle? AI is a powerful tool for such problems. Even if we cannot design clear rules, a data-driven approach can lead to probable answers statistically. We are developing a path detection AI model like the end-to-end approach. This model inputs multiple path images to CNN and connects them with LSTM unit. When we use these methods, data and annotation are really important. About data annotation, there are many different driving situations in the real world. When we drive the car, we understand something and decide our behavior. But if we cannot define it, we can't create the training data. For example, there are no clear lanes in the intersection. Which lines should be learned as the correct driving path? The driving path also varies depending on the drivers on snowy roads and roads without a center line, no center lines. Furthermore, the result of recognition changes each time depending on the environment, such as light condition. Regardless of the evolution of AI, such repeated data collection and annotations and tests are always the most important. This is the development cycle of AI. We are not just an AI developer, we are a car manufacturer. We build our own test cars with autonomous driving functions and drive every day. Data collection, data management, and model development, learning, and test drive. We control everything internally. This is our strength. Our team often says the car is the best teacher for us. Even the most stubborn engineers who don't listen to their bosses, but they recognize the problem by themselves when they are driving the car. Test drives are also very important for AI engineers. Let's watch a video of our autonomous driving car. In the snow road situation, this car only has a front stereo camera, no radar, no LiDAR, no map. Only stereo camera can control autonomous driving in the urban road, the mountain road. And while testing the autonomous driving cars, we have also developed a very large database system. Left image shows recorded data that can be searched with the load time and weather in our database. We have to try a lot of learning, so we use this system to manage which data is used for learning and which data for evaluation. Right image shows the results of our AI. The system has results from all software divisions, so we can compare the difference between each software. We built both on-premise and cloud environment for the training job. This image shows the architecture of our infrastructure of data pipeline, build pipeline, and AI training. And we use NVIDIA A100 GPUs to train our AI with a huge amount of data. And we create the pipeline which automatically build containers and start and the end training jobs. We have huge amount of driving data in on-premise storage, and we upload annotated images to the cloud to train our AI. This slide shows our cloud environment. We choose training environment depending on AI workloads. In early stage of AI development, we have to recreate training data frequently to support new methods, new models, because input-output formats change frequently. Last year, we built the data pre-processing pipeline on the Google Cloud by using Cloud Data Flow service to easily try new AI models and new data formats. On the other hand, we use the on-premise environment for heavy load training using a large amount of driving data. The final topic is development with CG. The camera sensor and CG technology are a very good combination. There are mainly three advantages. First is we can create the data with perfect labels and ground truth, such as accurate object distance and velocities. This is very important for AI development for training. Second is we can duplicate the same scene data with slightly different parameters, such as 30 meter, 31 meter, 32 meter. It is very important for detailed analysis of the problem. The last is we can create the edge case data that is difficult to record in an actual vehicle. For example, the collision scene. First example is the CG data with perfect labels. We create this data and use for AI training. Next example is the duplicating of the data. When we find some issues during the actual drive, we create the digital twin for deep analysis. We don't know if the problem is due to the weather or shape of the car, or distance. However, we can change any parameters with CG. Let's watch a video. The first is original image from cell camera. In the next step, we create the digital twin like this, and we change some parameters. This is a moving wall. This is very good target for testing because the surface is very flat, and to calculate the accurate distance. Finally, I will explain that the development of CG, creating pipeline. We are developing the pipeline that efficiently creates the CG using the recognition results from our cell cameras. Based on the detection results from eyesight, we create the 3D point cloud space with labels. We compare the detection results with the map data and place the assets in proper positions in CG space. And next, this video, CG creating pipeline. The first is detection results of eyesight, and this shows 3D point cloud from eyesight to depth data. The labeling data is also created by eyesight AI detection result. And the last is the digital twin data. And here is the conclusion. We developed SUBARU AstraNet AI with a very good combination of our camera. Regardless of the evolution of AI, repeated data collection, repeated annotations, and test driving are always the most important. We build automation pipelines for AI training in both on-premise and cloud to achieve more efficient development. And we utilize the digital twin generated from stereo camera data to develop eyesight and our AI. That's all my presentation. Thank you for attention.